Math 2414, Partial Fractions, Video 2, Requirement for Degrees. Before we jump into an actual example of integrating a rational function using partial fractions, I need to point out that there is a requirement before using this technique. And the requirement has to do with the degree of the numerator and the degree of the denominator. Recall that for a polynomial, the degree is the highest power of any of its terms. The degree requirement is pretty straightforward. If f of x equals p of x over q of x is a rational function, in other words, p of x and q of x are polynomial functions. I realize I just left out a parentheses. Okay, let's try this again. If f of x equals p of x over q of x is a rational function, in other words, p of x and q of x are polynomial functions, then we require the degree of p of x to be less than the degree of q of x. On that part, we require the degree of p of x, the top, to be less than the degree of q of x, the bottom, if we intend to integrate using partial fractions. Which raises the question, what happens if that requirement is not met? Had to do a little formatting issue there. If the degree requirement is not met, meaning that the degree of the denominator is not less, the degree of the numerator is not less than the degree of the denominator, then we use long division to rewrite f of x as s of x plus r of x over q of x, where s of x, quotient of the long division, and r of x is the remainder. Now, this is actually easier to do than it is to put into words, provided you remember how to do polynomial long division. All this is saying is, in order to try to integrate using partial fractions, the power in the bottom must be bigger than the power in the top. Let's take a look at these two examples and see which one's ready. In the first one, f of x equals x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. If we compare degrees, the degree of the numerator is 2, whereas the degree of the denominator is 3. In this case, the degree of the top is less than the degree of the bottom, so this one meets the requirement. Requirement that pretty much the bottom must have a larger power than the top. But if you'll notice on the second one, f of x equals x cubed plus x over x minus 1, the degree of the numerator is 3, and the degree of the denominator is the implied 1 on that x, and so this does not meet the requirement. Now, both of these are actually functions that we're going to be integrating in this series. And the first one is actually ready to begin the partial fraction decomposition process, whereas the second one is not. So, when it doesn't meet the requirement of having a greater power in the denominator, we have to use long division to fix that. So let's take this one, x cubed plus x over x minus 1, and remember how to do long division. Do long division. Well, first off, if you don't remember how to do long division, I have some college algebra videos that will review it. If anybody wants a link to those videos, just let me know. In the meanwhile, I'm going to do this long division as if it's a review, because frankly, it should be. We're dividing by x minus 1. We're dividing into x cubed plus x. One of the criteria for long division is if there are any missing terms after the highest power, you represent them with the 0 coefficient. After x to the third, we expect x squared. There are none in the numerator, so plus 0 x squared. After the x squared, we expect an x term, which there is, plus x. And then after the x term, we expect a constant, which there isn't. We have to fill in all the missing terms with the 0 coefficient. And then begin the division process. And I'm going to go through this fairly quickly. Again, if you want a review on how to do this in more detail, let me know, and I'll link you up to my college algebra long division videos. We start by dividing x into x cubed. X divides into x cubed to give x squared, which is equivalent to saying x times x squared equals x cubed. Then we multiply that times our divisor, and we write the product underneath the dividend. X squared times x is x cubed. X squared times -1 is -1x squared. This is the reason we needed the missing terms represented to make sure we have like terms lined up. Then we subtract. Now you got to be careful here because you're subtracting the entire expression, so watch your signs. X cubed minus x cubed is 0. These cancel. That was designed to happen. 0x squared minus -1x squared is 1x squared. And then just like in number long division, your next move is to bring down the next term, and then repeat. For our next move, we ask, what is got the eraser going there. What is 1x squared divided by x? You always divide by the leading term in the divisor. 1x squared divided by x is 1x, or more specifically, positive 1x. The equivalent to saying that x times positive 1x is positive 1x squared. Your goal on the top is to write whatever you need to so that when you multiply, you write it below here. The first terms match. 1x times x is 1x squared. I know the 1's not necessary, but it's there. 1x times -1 is -1x. Then just like in number long division, our next move is to subtract. 1x squared minus 1x squared is 0x squared. Those cancel. That was by design. And then x minus -1x is a positive 2x. All right, let's clean this up and do the next move. Actually, our next move is to bring down the next term. So we'll bring down the plus 0. Then do the division moves one more time. How many times does x go into positive 2x? Positive 2. Because when I do this multiplication, and by the way, these arrows that I'm drawing are for instructional purposes only. It's not necessary to draw them. Just showing you the flow of long division here. Positive 2 times x is positive 2x. Those match. We expected that. We designed that to happen. Positive 2 times -1 is -2. Now if we subtract that result, 2x minus 2x is 0, and 0 minus -2 is positive 2. All right, let's clean this up a little. After you've completed the last go around, dropping the last guy and then finishing on the rest of the moves, you have finished the long division, which means we are now ready to write our original rational function in a different form. In this case, our original rational function, the x cubed plus x over x minus 1, can now be written as the quotient, which is x squared plus x plus 2, plus the remainder, which was 2, over the divisor. This is just standard college algebra moves. Again, if you need some more assistance, if you're in my class, just send me a message in Canvas. If you're some random person in YouTube world watching this, post a comment below and I can link you to the college algebra video I have reviewing long division. I do want to go back and remind you what we were attempting to do. You're going to integrate a rational function, one polynomial over another. You must have a greater power in the denominator in order to try partial fractions. And if you don't, then use long division to rewrite the rational function as a polynomial. In this case, the polynomial is x squared plus x plus 2, plus a rational function that does meet the requirements for integrating by partial fractions.